All right, I'd like to take a look at these energy level diagrams that are in your reference table. So you'll notice you have two diagrams. You have hydrogen on the left and you have mercury on the right. So anytime you see an energy level question, you want to make sure that you're reading the correct diagram, hydrogen or mercury. Okay? So this is something that we looked at in the PowerPoint. It looks very similar. So you have the energy level over on the left-hand side, and then you have the energy over on the right. Now, one thing to definitely draw your attention to is the fact that the energy is measured in electron volts, right? That's very important because sometimes your answers can be left in electron volts. Oftentimes, what you will have to do is convert this to joules. Okay, and the conversion is on the front of the reference table, right? 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Okay. So let's look at using this. Right now, the key with this is to remember that electrons can jump from level to level. So they can go from 6 to 5, or they can go from 5 to 1, but they can't fall somewhere in between, right? That's why we use the Bohr model, that kind of planetary orbit, as our visual representation here, because they can't be in between states. So let's look at a question, right? You have a photon is emitted, right? So emitted means it's leaving, as an electron in a hydrogen atom drops from n equals 5 to n equals 3. And we need to find the energy of the emitted photon. So something else I'd like to point out to you is you have this tiny, tiny little section in your reference table. This is on page 5. Of modern physics, right? And so you just have some relationships here. This energy of your photon, right? That's a really great one to remember. This deals with Planck's constant. This is a constant on the front of your reference table. And then this is your energy of your photon. This one is used for your energy level diagrams, right? So this equation, E, energy of a photon, is the initial energy minus the final. So this is for your energy level diagrams. Right? And so that's what I'm going to use here. So I'm just going to write this down. The energy of my photon equals the initial energy minus the final. Right? And so this is different than what we're used to. Typically it's final minus initial. So I got to flip back to my energy level diagram. So we're going from n equals 5 to n equals 3. So I'm just going to write those values down. So my initial energy is in n equals 5, which is equal to, here's n equals 5, 0.54, and this is negative. It's a negative value. Right? And my final energy, we're in n equals 3, and this will be equal to negative 1.51, right, electron volts. And so now I can just plug in here. So the energy of my photon is equal to negative 0.54 electron volts minus a negative 1.51 electron volts. So minus a negative is like plus a positive, and that gives me the energy of my photon. Type this into our calculator. So negative 0.54 minus negative 1.51 gives me 0.97 electron volts. Right? So we could keep this as our answer. So I'm going to put a box around it. But let's just convert it to joules. Right? So we know that 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. So I'm going to convert this. Right? So I have 0.97 electron volts. I'm going to multiply by this conversion. Right? I want electron volts on the bottom because I want to get rid of them. So 1.6 times 10 to the negative 19 joules. Right? And so these are eventually going to go away. And that means that this energy of this photon is equal to 1.55 times 10 to the negative 19 joules. Great. Okay, so that's just an example of how to use those diagrams. Here's another one. So I want you to pause the video, see if you can figure out how to do this question on your own. This requires a few steps. So you're looking at an electron that's transitioning between energy levels, again in hydrogen, and it's going to cause the emission of a photon of visible light. Okay? And so you need to be able to figure out which of these transitions gives you emitted visible light. And you're going to know that it's visible light based on the frequency. Okay? So you know in your reference table you have that electromagnetic spectrum, and your visible light is broken down into these various frequencies. So you are looking for a transition that gives you this frequency. But our transitions really only give us the energy. So there's another equation you're going to use, right? And that is this first modern physics. The energy of a photon equals h, Planck's constant, times the frequency. So to find this based on frequency, you're going to have to use E equals hf, right? And the frequency is what you're looking for. But in order to do that, you need energy in joules. So you have to look at these transitions, determine which one of those will give you visible light. So pause the video, see if you can do that, and then click play again to see if you did it correctly. So right off the bat, you should be able to get rid of two answers here. If you're emitting light, that means your electron is falling down closer to the ground state, right? For light to be emitted, you have to fall down. So you are not going up in levels. So you're not going from 5 to 6 or 2 to 5. So you only have two things to consider here. Right? So I'm going to start with number 1. If we go from n equals 6 to n equals 5. So if I go from, let's just do n equals 6, we're going to go to n equals 5. That means that the energy of my photon is going to be, so first I'm going to use E equals initial minus final. So n equals 6. I'm going to flip back to my chart here. N equals 6 is negative 0.38. And then we're going to 5. So minus negative 0.54 gives me an energy of 0.16 electron volts. Now I have to convert that to joules. So I'm going to multiply by 1.6 times 10 to the negative 19. And that gives me 2.56 times 10 to the negative 20 joules. Well, that still doesn't tell me anything, right? So now I have energy in joules that I can place into this equation. So now I'm going to use E equals hf. So 2.56 times 10 to the negative 20 joules equals h. That's Planck's constant. That is on the front of your reference table. Right? H, Planck's constant, 6.63 times 10 to the negative 34 joule seconds. So 6.63 times 10 to the negative 34 joule seconds. And then we're going to solve for F. So when I do that, I get a frequency of 3.86 times 10 to the 13 hertz. Okay. So is that visible light? So if I go back to visible light, these are all times 10 to the 14. So no. So by process of elimination, it should be choice 4, but let's just quickly go through and solve for choice 4. I'm going to do this in a different color. So again, I'm going to start at the beginning. So E equals initial energy minus final. And we're going from n equals 5 to n equals 2. Right? So I'm going to get E equals n equals 5 has an energy of negative 0.54 minus n equals 2, which is negative 3.4. So this gives me an energy of 2.86 electron volts. And I have to convert that to joules. So I'm going to multiply by 1.6 times 10 to the negative 19, which gives me 4.58, let's round, 4.58 times 10 to the negative 19 joules. Okay, and so now I'm going to use that in E equals HF. So I have 4.58 times 10 to the negative 19 joules equals Planck's constant, 6.63 times 10 to the negative 34 joule seconds, and then we're going to solve for the frequency. So that gives me 6.9 times 10 to the 14 hertz. So let's hope that that falls here. 6.9 times 10 to the 14. So these are all 10 to the 14, and 6.9 would be in here. So it would be violet colored visible light. So that was from 5 to 2. So my correct answer here is choice 4. Okay, so a couple steps in that one. That's a great question. If you have questions on how to use those diagrams or those equations, please get in touch with me.